I'm Tonio, and I'm going to talk about goal-driven models of the sensorimotor system and their empirical inspiration. And I've been giving a short version of this talk already on Tuesday, but I hope to provide some additional details now that maybe spark more discussion afterwards, or like maybe also later today, and maybe even some opportunities for collaboration. But I will also, because not all of you were there on Tuesday, repeat some of the background. So first of all, when doing goal-driven modeling, it doesn't really matter in what domain you are, right? Like we are doing this in sensorimotor systems, but there's a lot of stuff on visual system as well. But what you always will do is like you're starting by building an architecture, include like on a macro scale. So including all the areas that you would like to include into the function that you are trying to model, and then building biologically inspired pathways through them. And what you're not doing is to actually set the connection strength between the separate neurons within these regions, but instead we are training this model because it is an artificial neural network, in our case, a recurrent convolutional neural network. So we are training this on a human task, on one that is ecologically valid and under humanoid constraints. For instance, given in our case, by this anthropomorphic robotic hand and the use of only humanoid raw sensory inputs. And then our premise is that given these constraints, the neurocomputational strategies that develop between all these different areas will have to resemble the neurocomputations that we would find in the brain, but that we cannot easily extract from the brain without having prior hypotheses. And if that's true, we can then go further with an analysis of these models that is easier than actually looking at the brain and then afterwards compare this analysis to human data to both validate, but also to generate new hypotheses that will in the end hopefully lead to a better understanding of whatever system we are trying to explore. Now, one important thing that I want to note is that only in this approach, only the model is biologically inspired, and it doesn't matter for our premise here whether the training is also biologically inspired or not, and we are definitely not training in any biologically inspired way. Now, before I'm going to show you what we are doing, maybe a bit short note on what has been done so far. Goal-driven modeling, as it was like traditionally done in the last, let's say, decade or so, and specifically since Yamins and DiCarlo really popularized this with their seminal paper, was mostly in the perceptual and specifically in the visual domain, where people have been building a lot of convolutional neural network variants, such as, for instance, the CORNET architecture, or also one dual stream architecture that will be presented in the talk after mine. But in the sensorimotor system, we have not so much work in with goal-driven modeling. One example would be the work by Michael et al., who put gloves on the hands of monkeys and then measured their grasping behavior as a response to their visual input, and then in a supervised manner trained a network to replicate this. And they could also show that the neurocomputations emerging were very close actually to what they could measure in the brain. However, the problem here is, of course, buying such gloves, getting the monkeys and all that stuff requires a lot of money and time, which is actually something that we want to avoid with goal-driven modeling. So what we are doing instead is to use reinforcement learning, where we do not need any data beforehand, but instead on the fly will simulate this experience, and the artificial agent will by itself develop a strategy through that. The problem with something like that, with reinforcement learning, and specifically with such complex models as we need them if we want to capture the entire sensorimotor system, and also as complex tasks as we do them in any sensorimotor task, but specifically here with in-hand object manipulation, is that it's quite an engineering effort to build a system that can do this, because it involves a lot of reinforcement learning methods, a lot of parallelization, and so on. So what we have done is for ourselves develop, of course, a framework with which we can do this, but we've also developed this with the idea in mind that other labs can profit from what we are doing if we develop it in a very open and easy to use way. So we've built this with a high level API, and we've called this Python library ANGORAPY, where you do not need to understand any details about the reinforcement learning methods that we are combining there, nor about how we are distributing this on high performance clusters, the simulation that we are using in order to simulate any of the tasks that you could use. But you really only need to build the model, train it very simply, and then in the future we will also provide functionality below the analysis. And this means that as the neuroscientist that wants to build this without understanding anything about the machine learning part, all you have to do is implement your model as a Keras model, so with TensorFlow, with two constraints. That is that the input to your system is a subset of the sensations, or like the sensory modalities that is available from the simulation in ANGORAPY, and that the output is some multivariate policy distribution over the actions, like that is over, for instance, the actuations on the joints of the robotic hand, and some valuation of the current state that the system is in. And it's not only easy to use, but although this is of course currently still like very inactive development, you can already access this and use it out of the box through our open source code on GitHub, but we've also containerized this, so you can just install everything with the dependencies and so on through a Docker image. But the most easiest way is probably to simply pip install ANGORAPY and give it a go. Okay, after this little advertisement, I will show you now how we ourselves use ANGORAPY in order to build a model and train it of the frontoparietal network to study human dexterity. And this model is depicted here. We will not go into much detail because I'm more focusing on how we inspire it. But you can see it captures the entire perception action loop. So we have the sensory cortices, the visual cortex, and so the visual cortex and the somatosensory cortex in order to build abstract latent representation from visual, proprioceptive and haptic information. And then we have both the posterior parietal cortex and the prefrontal cortex in order to both compare this to a goal description, but also to further integrate this information. And in the end, everything projects to the motor cortex, where we have the premotor cortex, which we model as a recurrent layer, so that entire motor sequences can be represented. And the primary motor cortex then will ultimately output this action distribution, the motor command, that is given back to the simulation. So how we are building this with macro scale plausibility is by first identifying all the areas in the brain that take part in sensorimotor processing, then basically putting them together, clustering them a bit to like arrange them, for instance, as the dorsolateral prefrontal cortex. And then we are using the Zebra Explorer in order to extract from the eBrain's multi-level human brain atlas information on how these clusters of areas are interconnected to build the pathways between them that we've seen in the form of arrows on the last slide. The problem with this is, however, that such structural connectivity really shows that in the end, everything is connected to everything. And we need some means of deciding what we include and what not. So what we are simply doing so far with a very heuristically chosen parameter is thresholding the connectivity such that we are ending up with only stronger connections between regions to be included in the model. In order to have these connections then also populated with actual like interneuronal connectivity that can model a function, we are training everything on in-hand object manipulation, which we have prototyped as the task of rotating and block, as you can see it in the hand on the slide here, with differently colored sides, and then also a letter on every side so that you can clearly identify in what orientation it is. So the task is to rotate this block into a target orientation as quickly as possible. And to formulate this, because we're using reinforcement learning, we need a reward. And this reward function in our case is simply the progress towards the goal at every time step that is made. as well as a punishment and a reward for dropping the block and successfully reorienting the block respectively. And within one episode, the hand, or the model rather, is allowed to do up to 50 reorientations, but needs to stick within a timer of 8 seconds. That resets, however, in case it achieved one goal. Now, the input that we are providing are recordings from a camera that is placed directly over the palm of the hand to model visual sensation. And then we have also 92 touch sensors distributed all over the simulated hand, as well as joint angles and velocities in order to represent proprioception. Now, training this results in the training graph that you can see here. On the x-axis, you have the training time. And on the y-axis, you have the average reward. And as you can see, our approach in blue that uses solely human sensation, as well as a plausible architecture, is quite competitive with the performance of the state-of-the-art in AI that you can see in orange here. And to give you an idea of how intensive it is to train such a model on such a task, here are some numbers. Like, to train this, it took about 48 hours of wall time, which equates to about 2 years of simulated experience. And this is possible because we are highly distributing this on CSCS by simulating on 384 CPUs and optimizing on 32 GPUs in parallel. And this is something that ANGORAPY also just does in the background without you having to care about it. Now, you can also see here an animation of the actual behavior then of the hand. And as you can, well, first of all, maybe more qualitatively, it can chain 40 reorientations now without failing to be within this 8-second timer I have mentioned before. And additionally, it also adopted quite human-like behavior, partially like, for instance, right now, where it uses the opposable thumb to rotate the cube around one of the axes. And then there's also some finger gating involved in order to rotate around the other axis. We are now in the stage where we are doing analysis. And very shortly, I want to give you one example of this here with in-silico decoding, where we've just shown that if you try to predict from the representations in M1 and PMC the orientation of the cube in 8 milliseconds, 80 milliseconds, and 400 milliseconds, respectively, you can really see how in PMC we have something like a plan building up, because the more in the future we want to predict, the better the performance gets. And then two last remarks. We have so far only inspired our model on structural connectivity, but there's also other options where we can really use data like the ones that many of you provide here. For instance, we want to use psychoarchitectonics to extract cell densities and sizes of different areas in order to inspire our model with regard to the relative sizes of the layers. That is the number of units there, as well as cell types, in order to also simulate cell types in the model by using unit-specific activation functions. And then as the very last remark, our architecture, but everything anyways, is always modularizable. So if you, for instance, are building a model of the visual system, we can very simply also plug this into our architecture and then see how it would perform on a sensorimotor task. With this, thank you for your attention, and I'm open for questions.